Hello and welcome to Logarithmic Functions. My name's Tuesday Johnson. Here's an introduction to the concept. I got the button right this time. All right, so logarithms define. No, we're not talking fireword here, not those kind of logs. A logarithm is a quantity representing the power to which a fixed number, called the base, must be raised to produce a given number. So if we have x equals b to the y, then that's the same as y equals log base b of x. Notice here, all y is an exponent. Y is equal to a logarithm because a logarithm is just an exponent. We make it look hard, right, by calling it a log, but it's just an exponent. So in words, y equals, this notation, right, says y is equal to the logarithm with base b of x. That's the definition. I prefer y is, clickety-click here. Y is the power I put on b in order to get x. All right, y is the power I put on b in order to get x. So let's look at some properties. For base b with b not equal to 1, our positive base, very important. B is greater than 0, just like it was in our exponential functions. Any positive number x and y and every real number r, the following properties hold. We have a product property for logarithms, and it's the same as the product property for exponentials. If we're multiplying two things with the same base, we add their exponents. All a log is an exponent. Quotient property says log base b of x over y equals log base b of x minus log base b of y. If we're dividing two things with the same base, we subtract their exponents, always numerator, subtract denominator. We have a power property that says log base b of x to the r equals r times log base b of x, and you know we've seen that before. A power raised to a power is multiplication. We have the identity in 0. What power do I put on b to get b? Well, we put the power of 1. We've seen this before, right? B to the 0 power equals 1. So log base b of 1 must be 0. It's just rewriting these equations. Our reciprocal property says that log base b of 1 over x is equal to negative log base b of x. Remember, all a log is an exponent. And when we cross that fraction bar, we change the sign. All right, so there's this guy, John Napier, in the early 17th century, and he came up with these things called logarithms. And logarithms was a great name for it at that time, but not so much anymore. We really need to just call them powers. The change of base property, however, was built into his system, and the change of base property for logarithms is extremely helpful because of our calculator use. Well, I wouldn't say it's because of calculators necessarily, but it's helpful now that we are using calculators especially. So the formula is log base b of x is equal to log base a of x divided by log base a of b. Notice that's the log of our new base, right? Whatever base we want to change it to. A has to be positive, however, and not equal to 1. Log of x, the x is already up higher, so it stays up. The b, it's kind of in the basement. It's a subscript. Log base b goes in the denominator. All right, change of base formula. We used to have to do logarithms with these things called Napier's rods, and then we had to use slide rules. I don't know who we are because I never did. But some special logarithms you might find on your modern calculating devices are the common log, and your calculator will most likely just have log, and that's assumed to be base 10. And then your calculator will have an ln button. This is an L. It's a logarithm. It is not an I. This is not n of x. This is ln of x. The lowercase l looks a lot like a capital I, but I can assure you this is ln of x. Two special logarithms that you'll probably have on your calculator. Now, with every new type of function, we want to look at the graph and check out the domain and the range. Logarithmic function has the form of f of x equals log base b of x, where b is positive, but not equal to 1. Here I have 4 different graphs. We see in black, we have log base 3 of x. So that's our base that's bigger than 1. y equals log base 7 of x. Notice that 7 is even larger than 3 as a base, and the graph is closer or lower, closer to the x-axis, lower. It's been kind of compressed a bit. In green, I have y equals log base 1/7 of x. So we see that fractional base values look different than base values where the base is larger than 1, right? Decreasing versus increasing. And finally, log base 1/4. For a smaller fraction, right? A larger denominator makes a smaller fraction. It's going to hug closer to the x-axis. Very interesting. Very interesting. All right. You're going to check out the next graph, right? We got some applications coming. Who doesn't like applications of logarithms? I appreciate you watching. I don't think I've asked you to subscribe lately, so why not? If I get to 1,000, I could do like full-on lectures live, and that'd be cool. But it's up to you. Thanks.